Hello and welcome. Today we're going to be looking at FRQ number 5 on the 2011 Form A of the AP Chemistry test. Some of you might notice that we have skipped number 4 on the AP Chemistry test from that year. That is because the topics that were on number 4 of that test are no longer being tested since the redesign of the AP Chemistry exam in 2014. So until then, we're going to be getting rid of one question for each year's test due to they having topics that are no longer covered. So we skipped number 4. Let's get started with number 5. If you like these videos or find them informative, please be sure to like and subscribe, and let's get into it. Alright, so our question here, we're told that hydrazine is an inorganic compound with the formula NH2H4, and we're told that in the box below, draw a Lewis electron dot diagram for N2H4 molecule by drawing all the electron pairs. Alright, so let's see how we're going to go about doing this. So, let's see. We can draw the H and we just draw on the electrons. So we have our 2 electrons there, 2 electrons there, 2 electrons there, 2 electrons there, and there, and there, and there. Right now, if you're thinking of this more as a conventional Lewis structure, but you can always draw it. You can also draw it that way, as in something that looks like this. Right, even though they told you electron dot diagram, you can still draw it the way in green. It really doesn't matter. Both of them are valid structures. Both of them work, and we can move on to the next part of this question. All right, part B says, on the base of the diagram you completed in part A, do all 6 atoms in the N2H4 molecule have are on the same plane? And we're asked to explain. All right, so are they on the same plane? So we can look back at these diagrams, and we see here that these N molecules, the nitrogen molecules, have 4 bonding pairs. They have 4 electron domains. So it's not going to be planar. Since if you have 4 electron domains, you get a tetrahedral shape, which is not planar. So the answer is no, since each nitrogen, each N, has 4 electron domains, making a non-planar tetrahedral shape. And that is our answer to this question. Don't know if you can see the tail end of that. It's supposed to say shape over here. It cuts off though. Alright. So since each nitrogen has 4 electron domains, it's going to make a tetrahedral shape, and that's non-planar. So that is not going to be planar, and we can keep going. Alright. Part C. Normal boiling point of N2H4 is 114 degrees Celsius, whereas the normal boiling point of C2H6 is negative 89 degrees Celsius. Explain in terms of the intramolecular forces present in each liquid why the boiling point of N2H4 is so much higher than the boiling point of C2H6. So actually, before we make a text box to start talking about what's going on here, the first thing you want to do on these kinds of questions is draw a Lewis structure of both of the molecules. So we have the N2H4, which is going to look something like this. We drew before, actually. That's going to look like this. And then on the other hand, we have the C2H6, which is going to be like this. All right. So we have those two Lewis structures now. We can start thinking about what we're going to be doing here. All right. So the hydrazine, right? Hydrazine, the N2H4 has what? Well, it has London dispersion forces, as everything does. Let's think bigger than that, right? So it's going to have dipole forces. Well, it has a tetrahedral shape. It has two tetrahedral shapes, right? So if we think about how this is going to play out, right? Because it has those electrons that are left out here. Then the pull of the hydrogens on the nitrogens are going to make it such that the hydrazine has dipole forces. So hydrazine has dipole forces. It has hydrogen bonds between the H and the N, right? So that's going to make hydrogen bonds, and then of course it has London dispersion forces, or LDFs, and then the C2H6, which is called ethane, I think. I'm not completely certain on that, but we're just going to call it that for now. Ethane has London dispersion forces. That's it, right? Because nonpolar, so it has a C and H bond, which are nonpolar, so it's going to not have dipole forces and not have hydrogen bonds. So then, since hydrogen bonds and dipole forces are stronger than LDFs, then hydrazine has stronger IMFs than ethane. So it is going to take more energy to break these bonds and turn the compound into a gas. So the the boiling temperature, energy to break the bonds of hydrazine. So the boiling temperature of hydrazine must be greater than that of the ethane. And that is our explanation. Now, you're probably not going to have to write that much, right? The main points to hit on here are that hydrazine has the dipole hydrogen LDFs, ethane has the LDFs, the hydrazine has stronger IMFs than ethane. Doesn't have, it's not because it has more IMFs, it's because it has stronger IMFs, right? There's a difference. And then that leads to the higher boiling point, the higher melting point in this, right? You can always justify it using this. Let's move on to the next question. All right, our next part, really. All right, so part D, write a balanced chemical equation for the reaction between dihydrazine and H2O that explains why a solution of hydrazine in water has a pH greater than 7. pH greater than 7. What does that mean? Well, that means that it's a basic. We're going to be creating a hydroxide, is what we're really doing right here. So we have N2H4. Actually, let's write it. Okay. We have N2H4 plus our hydrogen, and we want that to become a hydroxide. hydrogen becomes hydroxide. So we lost hydrogen, so the hydrogen is going to gain a hydrogen, and it's going to become N2H5 plus. And that is our equation. Let's keep going. Alright, part E. So we're told that hydrogen reacts in air according to the equation below. Hydrogen plus oxygen gas becomes nitrogen gas plus 2 gaseous waters, and the delta H is going to be negative 534 kilojoules per mole. And we're told that is the reaction oxidation reduction, acid base, or decomposition reaction. And we're asked to justify our answer. Well, let's think about what each of these really are. Alright, so a oxidation reduction reaction, right, is going to be where the oxidation numbers change. So how we're going to find that out is by simply like writing the equation and then writing down each of the oxidation numbers and seeing if they change. An acid base has to have a clearly defined acid and a base. Obviously, something is going to get protonated or deprotonated, and then of a decomposition reaction, you have one substance that's breaking into more substances. So it's not going to be a decomposition reaction because we already have two reactants, so that can't be decomposition. The acid base doesn't really seem like there is an acid in this entire thing, and there's no base either. So it seems like it should be a redox, right? Reduction oxidation. Let's see. Let's write the reaction out and let's see what we can do here. Alright, N2H4 plus O2, and that becomes N2 plus 2H2O. Okay. Now we're going to start writing down some oxidation numbers. So the H here, and mostly always, is going to be a +1, so the N2 is going to be a -2 for each of them. The O2 is going to be a 0 here since the net is 0. This is going to be a 0. This is going to be a +1. And this is going to be a -2 to balance that out. So we do see that we have some changes, right? This N2 goes from -2 to 0. This O2 goes from 0 to -2. So we do see changes in the oxidation numbers. So this is going to be a redox. Where do I write it? Redox. Actually, you can't see that. That's going to be a redox reaction. And our answer is that it's reduction, oxidation, or oxidation reduction. Does not really matter. And let's move on to the next question. Alright. So, we're said predict the sign of the entropy change delta S for the reaction. Justify your prediction. Well, what is entropy? Entropy is a measure of the possible microstate of something. And what you know about entropy? We know that entropy increases for gases. It's highest in gaseous states. It's in the middle for liquid states, and it's at barely anything for solids. So here we see we start with 1 mole of liquid and 1 mole of gas. We end with 3 moles of gas. So since gases have more possible microstates than liquids, and the product side has more moles of gas than the reactant side, then there is going to be an increase in the amount of possible microstates of the system as the reaction proceeds. Alright, now what does that mean? It means that basically, so the entropy will go up, so the change in entropy, which is delta S, is positive. It increases, so the change in entropy, the delta is positive. And we can move on to part G. Alright, part G, here it is. Oops. Part G says indicate whether the statement written in the box below is true or false, and we're asked to justify our answer. And the statement is the large negative delta H for the combustion of hydrazine results from the large release of energy that occurs when the strong bonds of the reactants are broken. Well, the first thing I see that's wrong with this statement is that when you break bonds, you put in energy. You don't release energy. You release energy when bonds are formed, not when you break them. To break the bonds, you have to put in energy. All right, that's how it works. And that's something I see that's wrong. So let's write that. Right. So we say the statement is false since energy is released when bonds are formed, not broken. Not broken. And that's something that's wrong. That's false with this statement. Also, we can see that looking at the equation for the combustion of hydrazine, we see that, well, the bonds in products, right? So like nitrogen gas is going to have a triple bond in there, right? So the bonds of the products are going to be way stronger than the bonds in the react, right? So the bonds in the products are going to be stronger than the bonds in the reactants. That's another reason why this statement is not true, since the bonds in the reactants are pretty weak compared to the bonds in the products. But that is why this statement is false, and that is it for this question. Hope you enjoyed this video or found it informative, and I'll see you next time.